Hey, and welcome to another video of Chem with Com. This is going to be the last video for gases, part three. Specifically, we're going to use the combined gas law and the ideal gas law. All right, this one's not too long, so let's get started here. Um, all right, here we go. All right, so we looked at four different equations last time, and we have an equation that does everything for us. So we don't have to memorize four. We can just take care of one and then we're all good. Let me just show you briefly. P1T1 is here. P1T1, P2T2. All right, I'm just going to circle one from now on, but V1T1 is here. We got P1V1 here, and we got V1N1 here. Everything, right? So basically what this is saying is that you have a certain value here, and when you change conditions, you'll have that same value here. So it's easier to explain. And remember, one is initial condition, two is final condition. P is pressure, V is volume, N is moles, T is temperature. Always bring this to Kelvin, right? All right, let's actually just use this equation to do some stuff that we did on the last section. And I'll show you what I'm talking about. All right. A sample of ammonia is found to occupy 0.250 liters, right? Under laboratory conditions of 27 degrees and 0.850 ATM. Actually, this is a new one. So the next ones I'll show you that it works for the old ones too. But this is a new problem that we're doing. Let's take a look, and it says find the volume of the sample at 0 degrees C and 1 ATM. All right. So this is a volume. So we'll call this V1. This is a temperature. We'll call this T1. Here we have P1, pressure, right? And it wants us to find the volume. So it's going to be our V2 at these different conditions. So this is going to be T2 and this is P2. All right, so we're going to use this equation. The only thing they don't mention is moles. So we're going to cut those out, and we don't need to use that because we don't have moles in this equation, in this problem. All right, V1, T1, P1, V2, T2, P2. Remember, one thing we have to do is get everything into Kelvin, but let's start here. 0.250 liters. 27 degrees C plus 273.15 equals 300.15 Kelvin. 0.850 ATM. V2 is what we're trying to find. This is 0 plus 273.15 equals 273.15 Kelvin. Last one is 1 ATM. All right. We're trying to find V2. So let's move this equation down. Remember, we didn't use moles, so we're going to keep those out. It's going to be P1 V1 over T1 equals P2 V2 over T2. We're looking for V2, so we're going to divide both sides by P2, which cancels this out, multiply both sides by T2, and that cancels out. All right, so I'm just going to flip this equation around. It's going to be T2 P1 V1 over P2 T1. These variables are easy to interchange and get messed up. That's where you're going to find a lot of these problems. So let's try to avoid that. And I'll probably make some mistakes, but hopefully we can catch those. 273.15 Kelvin times P1, which is 0.850 ATM. V1 is 0.250 liters. All right, all over P2, which is 1.00 ATM. T1, 300.15 Kelvin. Let's look at what cancels out. Kelvin cancels out, ATM cancels out. We're left with liters, which is exactly what we want. So now we have to plug all this stuff into a calculator. All right, let's try it. Let me open up a calculator. All right. 273.15 times 0.850 times 0.250. And then I'm going to say divide by, but I'm going to put it in parentheses. So we're going to do everything underneath. And it's 1 times 300.15 850,250. All right, close parentheses and then enter. I got 0.193. 0.193. All right, 0.193 liters. Let's see, we have 3 sig figs here, 3 sig figs here, 3 sig figs. So I think this is it. 0.193 liters. Let me just make sure we're doing this correctly. Yep, looks good. All right, and now on to the next one. All right. All right, so here's one we did before, but I'm going to show you it works for these other ones too. All right, so sample of gas has a volume of 30 mils. If you want the other equation, go back the last video and I show you how to do it with the other equation. But this to me is more useful because it does all of them and you can just cancel out the stuff you're not using. All right, 30 mils, it's a volume. 6.5 psi, that is a pressure. Determine the volume. So we're trying to find V2 and pressure is 11 psi is P2. Okay, so we're only using volume and pressure. We're only using volume and pressure. We're going to cancel everything else out. And look, we have the same equation. P1, V1, P2, V2. P1 is 6.5 psi. V1 is 30.0 mils. P2 is 11.0 psi. V2 is we don't know, right? P1 V1 equals P2 V2. We're looking for V2. Divide both sides by P2. So I'm going to rewrite it, just swapping the positions. So it looks easier for us to do on a computer. All right, P1 is going to be 6.5 psi. V1 is 30.0 mils divided by P2, 11.0 psi. All right, so let's, psi cancels out, 6.5 times 30 divided by 11. So let's do another one. 6.5 times 30 divided by 11. All right, 17.7. It ends up being 18 milliliters, I believe. 18 milliliters. That's going to be V2. All right, so same answer, different equation, but when you modify it to fit your specific equation or your specific problem, it ends up being the same equation. All right, let's do another one. This again, we did this last chapter, but use a different equation. I'll show you how this is the same, and you can just use one equation instead of those 4. 12.8 liter volume of gas contains this many moles, which is N1 at constant temperature and pressure. If temperature and pressure are the same, we don't use those. V1 over N1 equals V2 over N2. This here is N2. We're looking for volume. This is what volume? V1, N1, V2, N2. V1 is 12.8 liters. N1, 0.000498 moles. V2, we don't know. N2, 0. Then there's 4 zeros. 1, 2, 3, 4. 136 moles. All right. We're looking for V2. So we multiply both sides by N2. I'm going to swap positions. So V2 equals N2 V1 over N1. Plug the numbers in. N2 is 0.0000136 times V1, which is 12.8 liters, divided by N1, which is 0.000498. Sorry, this is moles and moles, but those cancel out. So we have V2. You have to plug this one in. Okay, is clear. 0.1234136 times 12.8 divided by 0.123498, I believe. Hopefully, yep, there you go. So we got 0.350 liters. All right, so again, same exercise, same question from last subtopic, right? It was like the gas laws, but we use a different equation. We customized it for our specific needs, and it worked out perfectly. So again, try to use this one equation for all, and it'll make your life easier. I mean, imagine having to remember one equation instead of 4 equations. To me, it's a lot better. All right, next. The ideal gas law. This relates a bunch of different variables: pressure, volume, moles, and temperature. Let's look at this. We saw this in the last section, this in the last section, this in the last section. There's another one, but it was, pretty much the same. So, but look, all the V's are on the left side. All the P's are on the left side. All the T's are on the left side, right? And all the N's are, sorry, on the right side, and all the N's are on the right side. So you put them together and you get P, pressure, and volume are proportional to moles and temperature. All right, this is again from last chapter. We're consolidating these things now to make one equation, and the equation here is the ideal gas law. The only new concept here is we're putting in R, which is a constant. This helps you convert back and forth and kind of manage all these units, right? We have volume in liters, pressure in ATM, we have moles in moles, and we have temperature in Kelvin. So we insert that R here, and that lets pressure and volume equal moles and temperature, only by using this gas constant called R. And there's a few other constants that we'll learn along the way, but actually, yeah, but this is it for now. All right, so this is what we're going to use, and this is how to relate, again, pressure, volume, moles, and temperature together. All right, so let's try this out. Methane, CH4, is being considered for use as an alternative automotive fuel to replace gasoline. 1 gallon of gasoline could be replaced by 655 grams of methane. What is the volume of this much methane at 25 degrees Celsius and 745 degrees torr? Let's check it out. We're going to use the PV equals nRT. Let's write down all the variables. P, V, N, R. T. You might not even know you're supposed to use that. So let's actually explore how to figure out if you need to use that. E, pressure. We have T. We need V. But what else do we have here? Right? We have grams. What good does that do us? Well, remember, if we have grams, we could always convert to moles. So then we have pressure, 745 torr. We have we're looking for volume. We don't have moles, but we have 655 grams, and we're going to change that into moles. We have R 0.08206 liters ATM over moles Kelvin. Temperature is 25 degrees C. But we need things in ATM. We need things in Kelvin. We need things in moles. So we're going to have to do a bunch of conversions. This is plus 273.15. That's going to be 298.15 Kelvin. We know there are 1 ATM for every 760 torr. Torr cancels out. Let's do this. 745 divided by 760. 0.9803. 0.9803, and this is ATM. All right, now this takes a little more work, and we have to figure out methane. So we have carbon, we have one of those. Each one of those is 12.01 grams per mole. Hydrogen, we have 3. Each of those is 1.008 grams per mole. Let's do the math. So let's clear this. Parentheses 1 times 12.01, close parentheses, plus, oh, I think there's supposed to be 4 hydrogens, my bad, CH4, right? So CH4, so we have 4 times 1.008, close parentheses, and we have 16.042 grams per mole. All right. So we know grams have to be on the bottom, 16.042 grams of CH4 per 1 mole CH4. Grams cancel out, right? And so we have 655 divided by 16.042. 40.830. So 40.830 moles. All right. Let's do this. We're looking for V. So PV equals nRT. If we're looking for V, we divide by P on both sides. That cancels out. So it becomes V equals nRT over P. N is 40.830 moles. R 0.08206 liters ATM. I'm going to make a big old line here. Moles Kelvin. Temperature is 298.15 Kelvin. Pressure is the last thing. 0.9803 ATM. All right, let's cancel stuff that will cancel. Moles and moles. ATM, ATM, Kelvin, and Kelvin. We're left with liters, which is perfect because that's what we looked for. All right, now it's a bunch of math. 40.830. So let's do this one. Clear. 40.830 times 0.08206 times 298.15 divided by, what's our bit? I guess we can't. Let's put all this in parentheses. We can do it without it. I just want you to, it looks a little better with them just when you're learning. So let's do that. Again, if you don't have to do it this way, 0.9803 times, oh, that's it, 0.9803. All right, so we have to remove that parentheses now and that multiplication sign. So it looks like that, right? So it becomes 1,019. It's a big number. We have, let's see here, 3 sig figs here. We have 4 here, we have 3 here, and then we should have 3 here. So we should have 3 sig figs. It's hard to turn that into 3 sig figs, right? So it's going to be 102. Oh, that's actually 3 sig figs there. So 1,020 liters. All right. Let's check that out. There you go, 1,020 liters. All right. Let's do it. So let's do another one. Let's see here. I get over there. All right, let's move on to this next one. Same process. Let's explore the problem and then find the appropriate equation, plug it in, convert. All right. All right, calculate the pressure. So we're looking for pressure in bar. P. We have moles. We have a temperature. And we have a volume. That's how we know it's PV and RT because we have a pressure, moles, temperature, and volume. Let's write these all out. PV, N, R, T. Pressure is, we're looking for that, and we'll just do a parentheses bar so that we remember how much that is. And we should figure out how much that is in the next slide. So this is volume is 180 liters. Moles 2520 moles. R is 0.08206 liters ATM over moles Kelvin. Temperature is 27 degrees Celsius plus 273.15 equals, that looks like 300.15 Kelvin. I think we're done with conversions. So PV equals nRT. We're looking for pressure, so we have to divide both sides by volume. That cancels out. Let's write it down here. P equals nRT over V. N is 2520 moles. Again, I'm going to make that long line. Times 0.08206 liters ATM moles Kelvin. Temperature is 300.15 Kelvin. On the bottom is volume, 180 liters. Let's do the cancellations. Liters, moles, Kelvin, ATM is left, which is perfect for us. All right, now we have to do our calculator. Let's clear this. I'm going to do open parentheses, 2520 times 0.08206 times 300.15, close parentheses, all divided by 180. I got 344.8. And what? ATM. All right. So what we have to do here, since it wants it in bar, is we have to convert that to bar. We don't have a direct conversion there. Let's find bar here. Looks like we have to go from ATM to pascals to bar. Okay. Oops, so let's do that. We have 340 ATM. We need ATM on the bottom, so it's 1 ATM equals 101,325 pascals. Then we have 100,000 pascals equals 1 bar. All right, and then I guess what appears 1 bar equals 100,000. All right, so then let's do the canceling thing. ATM, ATM, pascals, pascals, we have bar. So now we have another set of things we have to put into the calculator. Let's check it out. Let's use this one now. It's clear. 344.8, oops, 0.8 times 101,325 times 1 divided by 100,000. And I got 350. Let's just make sure, right? We have 3 sig figs here, 4, 3, 2 actually. So here should only be 2. So this is 2 here. We have, those are infinite. So then we have 2 here. So it should be 350 bar. Yep, that was the right answer. All right. So now let's finish up. I wanted to give you a slide that holds everything in one slide for gases. So here are all the units that you could use to, all the conversions you could use and the different pressure units. This is the combined gas law. Remember, only use the variables that change or cancel the ones that don't change, right? That stay constant. This is the ideal gas law. This is the R constant, and this is how to convert from Kelvin to Celsius. All right, that wraps it up. I'll catch you next time for our last topic called acids and bases. All right, have a good day, and I will see you next time. Thank you very much.